Okay, it's ready.
Okay, thank you. I see that just Nicholas come in. So it's okay.
Hi already. Sorry.
Hi, Nicholas.
I'm supposed to introduce, but go ahead, you do it.
Yes, I will do it. Michelle, it's okay if we begin now?
Oh, sure, yes.
Okay. So it's my pleasure to introduce you Michelle Beetz, which is a professor of computer science at Bremen University and the head of the Institute for Artificial Intelligence at Bremen. The Institute for Artificial Intelligence investigates AI-based control methods for robotic agents with a focus on human-scale everyday manipulation tasks. For example, with OpenEase, a web-based knowledge service providing robot and human activity data. They aim at improving interoperability in robotics and lowering the barriers for robot programming. So you will see in the presentation, his research interests include plan-based control of robotic agents, knowledge processing and representation for robots, and integrated robot learning and cognitive perception. And another thing that is good to know is that most of the results of his group is provided as open source software, primarily in the WOS software library. And also we are working together in the framework of this very interesting project, AI for HRI. So thank you, Michelle, to accept the invitation, and I'll let you the room to do your presentation.
Yes, thanks a lot for inviting me, and thanks a lot for having me there. And it's always a pleasure to work together with you, and we are enjoying it a lot. Yeah, so I want to talk a little bit about autonomous robots accomplishing manipulation tasks, and how AI technologies can help the robots to do that. The problem that I'm most excited about is accomplishing an everyday activity, which for me means that we give a robot a very underdetermined manipulation task request, something like clean up. And the task of the robot control system is to take this underdetermined task request and turn it into a specific body motion of the robot that achieves the desired effects and avoids the unwanted ones, right? So it's, I mean, if you are a robot control program, the only thing you can do is move the body of the robot, right? And that's the only means you have in order to accomplish manipulation tasks. And the big problem is, yes, how do you actually fill in all the knowledge that you need in order to do the tasks right, without this knowledge being explicitly stated. So we are looking at this kind of task in the context of the EVE household marathon, which is a challenge task. It's basically the robot accomplishing everyday activities. So it's kind of setting the table, kind of eating is part of it, then cleaning the table, loading the dishwasher, unloading the dishwasher, extremely simple meal preparation, and then it starts again, setting the table, eating, cleaning, and it does it for 3 meals a day, so breakfast, lunch, dinner, and it should do it essentially for many robot days, is essentially a lifetime of a robot. And that's kind of the challenge we want to kind of manage. And if you are looking at these tasks, setting the table, cleaning the table, it's always a task, put objects where they belong to, right? And it's essentially, it's just a loop, and and it's basically the action that is to be performed in the loop. Take the next missing item and put it where it belongs. Okay, so let's see how we are doing that.
Hi, my name is Gaia and I'm a PhD student at the Institute for AI at the University of Bremen. In this video, the PR2 is performing the household marathon demo of the EASE project. The idea of the demo is that the robot executes different variations of mobile pick and place, whereby it needs to act completely autonomously with the minimal amount of human interference. The first task is to set a table for cereal breakfast for one person. This involves 5 objects: a bowl, a spoon, a cup, some milk, and a box of cereal, which have to be brought to the dining table. Afterwards, the table has to be cleaned up, so the washable objects are placed into the dishwasher, the cereal box is placed back into its storage location, and the milk box is thrown away into the trash, as it's assumed to be empty then. The perception system that we use is called RoboSherlock. It employs an ensemble of experts approach based on the principle of unstructured information management. Importantly, it works in assumption-free scenes, which means, for example, that we don't expect a supporting plane to exist for each object. This is required, for example, for the objects in the dishwasher or in the door of the fridge. The motion control framework that we use is called GISCARD. It does whole body control. For the PR2, this means that we control the arms, the torso, the base, and the head simultaneously. It uses a constraint and optimization-based approach with which we can define multiple goals at the same time. For example, grasp the object while looking at your hand, staying away from the joint limits, and avoiding collisions with the environment. The plan executive that we use is called CRAMA. It uses the reactive planning approach such that the plans concurrently perform the motions and monitor their execution. Simply put, this means that if a failure happens, such as an object slips from the gripper, the robot reacts immediately. The sequence of actions and the failure handling strategies are engineered according to a general model of mobile pick and place, and the parameters of actions are inferred at runtime by querying the knowledge base. There are a lot of challenges that need to be solved in order to master these mobile pick and place actions. First, the robot needs to have an enormous amount of knowledge about its environment, the task, its own capabilities, the user preferences, the physics of the world, and common sense rules. Second, the robot needs to be able to execute its actions in a wide range of variations. For table setting, this means that it should be able to get any object from any location in the environment and place it at any other plausible location. The robot also has to deal with the non-determinism and the partial observability of the world, which simply put means that acting in the real world very often leads to failures, and the robot needs to be able to recover from them. And it needs to keep its beliefs about the world in a consistent state, as close to the state of the real world as possible. Finally, in order to reach human-level skill and mastery, the robot needs to be able to improve its performance over time based on collective experience. For more information, please follow the links in the description below.
Okay, so this is what the system is doing. And the main computation task is the task of contextualizing underdetermined action descriptions. So I will introduce basic components of the system and how it works. And so the system basically uses as its main data structures a generalized action plan, which can be refined autonomously by the robot into a specific motion plan. And this task is mainly filling in missing information into the plan through contextualization. So the robot takes its information about the situation it's seeing and its background knowledge, something like eggs are breakable, and it basically uses the knowledge in order to specialize in the motion plan in a way that it can achieve the desired effects and avoids the unwanted one. And that's kind of just the computation tasks that we want to achieve. So let's just look at the different components very briefly. So the generalized action plan, so we assume to have a generalized action plan for each action category. So action categories are things like fetch and place, cut, pour, wipe, and things like that. So a generalized action plan has formal parameters. So like the object that is to be transported, the destination, and the body of the action plan is formalized in a very abstract way. So we can simply say, with the robot being at a specific location, perform the action fetching the object, so which is it's supposed to fetch, and at the location, which will be the destination, perform the action, place the object at the right place, right? And so what the game that we are playing is that we allow the programmers of robot control systems to do a lot of hand waving to basically specify actions in a very abstract way. And then the robot control system is doing the specialization of these abstract terms at execution time in an autonomous manner. So the purpose of this contextualization plan process is to parameterize a motion plan. We take as our template of how motion plans should be structured a model that comes from cognitive psychology, in particular from Flanagan and his colleagues. And this says something like picking up an action consists of the phases of reaching for the object, lifting it, transporting it, and releasing. Each of these phases has a sub-goal that has to be achieved. So reaching has the goal of the hand being in contact in the object, lifting, the object being lifted off the supporting surface, and so on. This model is specialized in our system, and the specialization and refinement is necessary to make it executable in a robot control system. And so we have essentially more motion phases that correspond to the one of the Flanagan model. And each of these motion phases, they have parameters. And if we basically assign values to all the parameters, we have a specific robot motion. So the contextualization process is started by giving the robot a task request. So a task request might be something like perform an action of the type fetch and place, where the object is an object of the type cup, and the destination is a location which is on the kitchen table, right? So when it gets this task request, it basically expands the body of the generalized action plan. So it's kind of in the first phase, just doing that. And then it's extending that instantiated plan with the parameters of the motion plan, right? And then the only thing the plan executive has to do is it has to query the parameters of the motion plans, and in a way that it asks for values of these parameters of the motion plans that are sufficient for the action fetching the object at a particular location to be successful. So we just want the parameter for which the robot thinks the body motion will be successful in getting the cup to the kitchen table. So many of the community today look at that kind of task as a mapping, right? A mapping of the object, the task, and the environment, and maybe kind of the context into specific behaviors that are suitable for the different combinations of object, task, environments. And if you're looking at this task as the contextualization as a task mapping from this to this, then you can turn it into a learning problem, right? So you can basically take a demonstration that we have seen just now and basically ask for every combination of object, task, environment, state, and context, what is a behavior that is successful in order to generate the right behavior, right? And you can do that by basically turning that in a data-intensive machine learning problem and basically learning this mapping as end-to-end mapping from these parameters into behaviors. So we are not going this way. So for us, kind of the big challenge of contextualization can be seen if you're looking at that problem, right? So you get an underdetermined task request, pour the water out. And the concrete situation the robot is confronted with is a pot with a hot pot with vegetables, water in it. And in this context situation, the robot has to compute constraints on its body motion. It basically has to infer that it has to grasp the pot by the handles, hold the pot horizontally, tilt the pot around the axis between the handles, hold the lid while pouring. And in order to execute the action robustly, it basically has to compose these constraints in order to synthesize behavior that has a good chance in accomplishing the respective tasks successfully. So this goes beyond the capabilities of kind of these data-intensive machine learning mechanisms. So instead of that, so we are not basically looking at an end-to-end black box that kind of learns the mapping, but in our approach, we advocate that this mapping should be realized by a cognitive architecture, kind of a complex computational system with many cognitive components, which is inspired by the different components in the human brain that are supposed to kind of contribute to the mastery of manipulation actions. And essentially that cognitive architecture consists of the plan executive that we have seen in the introduction, a knowledge representation and reasoning system that is able to answer all the questions that the plan executive is asking in order to specialize the motions, and a metacognition component which is able to do introspection and self-programming on the plans that the robot uses. And we have a perception component and motion control executive, as we have seen in the video. So the basic constellation of our system is that we have that generalized action plan and we run it with a hand-coded knowledge base. And in the hand-coded knowledge base, there are generalized knowledge chunks encoded in symbolic representations. And the examples of these knowledge chunks are cups used for table setting have to be clean and unused. People might have preferred cups. Clean cups are in the cupboard. Cups have to be grasped at the outside, and so on. So what we were successful in doing is we could show that we could provide such a hand-coded knowledge base, as we have seen in the video, that is effective and sufficient in order to do the table setting task and the cleaning task. So this configuration of the system basically has leads to a lot of failures, local failures that the robot recovers from. But it's essentially an effective mechanism to solve the challenge plan. And we could show that if we take that basic system and we add prospection, so looking into the future, we can be substantially better than the original version. So this enables the robot to do things like it's already grasping an object in a way that it can put it down without regrasping. In the second branch, we were basically looking into if we have that hand-coded knowledge base and we have lots of log files experience of executing this, can we use the experience of the robot in order to learn better parameterizations of the plan? And again, that is that has been shown to be sufficient for substantially improving the basic plan. We don't need to use the experience of the robot itself, but we can also learn from observation, for instance, from people showing how the tasks should be performed in virtual reality. The cool thing about people demonstrating the task is that the people have lots of common sense knowledge, intuitive physics understanding, and therefore the robot can learn much faster because it has kind of more informative examples in the experience. The problem is that it has to transfer the experience from the capabilities of the human to its own capabilities, which makes it kind of more difficult to transfer. We can also improve the plans by adding transformation learning and transformation planning. So here the idea is that instead of kind of transporting objects one by one, the robot could use a tray and thereby do it more efficiently, or it could learn abstract knowledge from other robots, and again, that would improve the behavior sufficiently. So we have that basic plan, and we have lots of cognitive capabilities, namely prospection, learning from experience, learning from observation, transformational learning, and learning abstract knowledge. And we can show that all these mechanisms improve the behavior performance of the robot. So kind of the open challenge that excites me most is open-ended manipulation task learning. So in the end, you would want the robot to read instructions in the web, to watch instruction videos, and perform task learning by that. So this is kind of much more challenging than the tasks that are accomplished through deep learning, because in deep learning, you typically go for a task and you learn kind of a very good performance for that task. But here you have to learn the task itself, right? And you also kind of want to learn by watching the videos, not only the plans and how they should be parameterized, but you also want to extend your predictive modeling capabilities, your prediction capabilities about what will work and what not, because that helps you in solving tasks that are novel. And of course, you also want to improve the task performance. But that's, I think, the kind of the challenging task a robot really has, a learning task that a robot really has to do. And the amazing thing is that humans can accomplish that learning task by one-shot learning, right? They just see it and they do all these kinds of things, and they do it right in one learning step. Okay, so, and I think, so this is basically our hypothesis, that if you are pushing into that direction, so you need a different kind of knowledge representation and reasoning system. So, I mean, in a way, what you want to learn in your learning process is a predictive modeling and knowledge representation and reasoning engine. You want to basically be able to have an inner world model that functions approximately like the outside world, and that you can look with your inner eye at, and it basically looks the same way as the world of the outside, right? And this inner world model, which is the component of the predictive predictive engine, it's basically machine understandable. And we make it machine understandable by having an ontology and axiomatizations formulated in a first order logic representation for each of the entities that you see here, and even entity parts that you're seeing here. And the whole predictive engine is made machine understandable by wrapping it in a logic-based language, essentially a language which looks like a Prolog knowledge base, but most of the predicates you're using in the language, they are not kind of simple structures stored in a symbolic knowledge base, but they are computed on demand out of the detailed data structures available in the inner world model. And I will talk about how that is possible. So let me summarize. So what we want to have as a knowledge representation and reasoning system for an autonomous robot is a predictive modeling and knowledge representation and reasoning engine that can imagine, model, represent, explain, predict, transfer, and plan underdetermined action descriptions and their execution based on an inner world model in a machine understandable manner. And the reason we want that machine understandable manner is that the robot has to do open question answering regarding to all questions it has to ask that are required for a successful action execution. So the logic-based interface that the robot is using is a Prolog language, and it just has some syntactic sugar that at the high level you only have 3 predicates. So you have that a relation P SO holds during a certain time interval I. You have occurs SI, essentially that an event occurs during an interval, and you have entity description. So you can basically say that there exists an entity that satisfies a certain description. And I will also heavily use a predicate that show a certain structure at a time instance. So using that language, we can, for instance, formulate a query. We are looking for an entity which should be an action, and it should be an action of the type grasping, and the object acted on is an object of the type spoon, and that action should occur in the time interval starting at time instant A and lasting until time instant B. And that spoon should be on top of a table, and the table is an entity of the type stable, and we want to show the spoon. So that gives you just a feeling of the kinds of queries we can build with that language. So how the robot uses that is, so for instance, it can ask a question, basically, I want to have an action where I put down an object, and I want to basically look at the sub-action where I release the object, and I want to look at the time interval where that occurs, And I want to basically see the trajectory of the gripper during that task. And here the yellow line is essentially that trajectory. And the robot, the plan executive, gets back all the bindings kind of these variables, which enable it to kind of execute it in the more low-level system components. So let me show you how powerful that language is by running it on scenarios coming from virtual reality demonstrations. So here we have a query. We are looking for an action of the type pick and place, and where an object is basically picked up and placed. And we want to see all the sub-actions in the Flanagan model, and we want to show them in different colors, right? And that's kind of what the what the answer of that symbolic query is. So it gives you the sub-symbolic data structures. So here you have another question. So you basically look at actions of the type grasping something, and where you basically grasp a handle, and you want to show the gaze of the human in that interval in the color green, right? And you see here where the human looks while grasping objects. Yeah. Here it's basically the same kind of thing, but now we are looking at contact events where basically kind of handles are in contact with the food, and then we see these are closing events for containers. Or we can basically go for the trajectories for picking up kind of the cereal box, and we show them in yellow. And the trajectory, so this is from multiple episodes. And here in blue, we have the same trajectories for the milk carton that is put on the table. So again, I think it should be obvious that the way we are doing it is that we can autonomously create machine learning problems out of the symbolic representations we create for these scenarios. So here we basically show the pose of the object through an arrow, and we basically see that in the dishwasher, cups are put down upside down, right? And we can look at the trajectories. And so essentially, every component of a manipulation action can be kind of extracted using symbolic queries and allows the system to have access to all information it needs. So the reason that you want to have symbolic reasoning in your robot control system is that, again, if you're comparing to machine learning methods, you want to represent knowledge through modular, composable, generalized knowledge chunks, right? And this basically gives you a lot of robustness against novel situation. So when I tell you, imagine that you are driving a car and in front of you is a giant egg that you are about to crash into in 2 seconds, right? So all of us can imagine how that looks when we are crashing into a giant egg, even though none of us has actually any experience, I assume so, in doing that. So I think it's clear that humans have mechanisms of imagining things that are clearly outside the training data and that require to compose different components of experience in order to form expectations about these novel things, right? And the other cool thing about symbolic reasoning is that it gives you a mechanistic way of manipulating symbol structures so that you can solve semantic reasoning problems. And you can be sure if your reasoner gives you an answer that this answer is right, given what you basically have axiomatized as knowledge, right? Very powerful mechanism in your system. But if you're just using symbolic knowledge representation, this knowledge is far too abstract to actually generate motions out of that representation, right? So you want to have more detailed representation that involves kind of physics parameterization, but also the geometry of objects part, and everything else. So if we are looking into the last years, so we have seen huge advantages in virtual reality technology and in particular game engines, which essentially give us that. So what we are doing is what is a simple and very fundamental idea that we are doing is that we are using the symbolic names in our symbolic expressions, and we link them to data structures in the of the virtual reality scene graphs. And if we basically have a subtree in the virtual reality scene graph that contains all the information that is needed in order to render the represented objects, also to physically simulate that kind of object when putting forces on that, right? So, and that's kind of a very cool thing. So kind of the very important part is if your symbolic names in your symbolic representation are linked to data structures in virtual reality graphs, that gives you the detailed representation you need for computing motions in robot control systems. It also gives you a grounding of the symbolic representation, which is also very important. Because the virtual reality scene graphs are used or come with physical simulation and visual rendering engines, so we get very powerful reasoning mechanisms from the virtual reality infrastructure for free. So this is mental simulation, so we can basically execute a plan that we have in mind on the scene that is defined in the virtual reality graph, and we can render basically, if we put a virtual camera somewhere, how a virtual reality graph looks from the point of view of this camera. Another thing is that, which is very cool, is that these virtual reality engines, that they are capable of managing and maintaining these extremely detailed and realistic models in real time, which is also a property that robot control systems need. So the next thing is the question of, so how can we actually cast these data structures that are inside these game engines such that they are virtual knowledge bases for the robot, right? And the technique is quite simple, right? So we are defining in a language like Prolog predicates, for instance, like the expected image, which basically is true for the image the camera would see in the current situation, right? And the way we are implementing these relations is through computational processes. So the predicate expected image calls the rendering engine with the robot camera specifications and the pose of the current pose of the robot camera. It and then it can return the image you would expect to see when the robot captures an image with its own camera, right? But because kind of the knowledge base, kind of the virtual reality scene graph is at the same time a rendering of a symbolic knowledge base, we can also play very kind of powerful operations. We can execute powerful operations. So for instance, we can basically assert that the milk box is the only visible object in the scene. So all other objects and object parts are invisible, and then we get a perfectly segmented image of the milk box, right? Or we could define that every object and object part in the image has a different color. And then the color is unique for the ID of the object part, right? And we have a one-to-one mapping from pixels to the object they depict and back, right? It's kind of a very powerful mechanisms for grounding symbolic representations.
Michael?
Yes.
I have a question about, I mean, this seems hard to us to do this linking between the virtual reality and the symbolic, the first order logic. I mean, are you hard coding that, or are you actually trying to learn that? We're trying to actually learn that, and we think it's a pretty hard problem.
Yes, so I mean, at the moment, we make the assumption that we know all objects in the world a priori, and we have models of them. So what we are doing is we are synthesizing essentially the belief state out of known objects of the robot, and then we render it and we compare it to the image that the robot is seeing. So it's kind of, we are doing it, I guess, a bit the other way around. So the robot basically tries to create a belief state with its inner world model that matches what it sees. And so the counting is just to the inner world, and it's not to the outer world. And I think that somehow makes the problem much more feasible. And we are also not making the requirement that the inner world model kind of correctly represents the outside. We rather consider the inner world model as a resource to kind of compute the successful action parameterization, which I think is also a weaker assumption, right? Because when the robot executes it, it always kind of debugs the belief state, and if it's wrong, it just continues with a better world state. And I think I will show some more visualizations of that, and probably we should come back to that afterward. And I think.
Sure.
Yes. Okay, so one of the things that happens is when the robot executes a robot plan, that when it executes the robot plan, it also executes it in its belief state at the same time. So here in this image, the lower part of the video shows the real world. The upper part shows the belief state of the robot. So here you see the robot executive grasping the object, picking it up. And so when it's actually doing that, it's only very seldomly that it updates the belief state with the camera images, but it basically executes it in the physical simulation. So it basically here attaches the hand to the object, and then it basically updates where the cup is based on its inner world model rather than the outside. And you see, again, that's kind of cool because you get information about where the cup is in situation where the perception problem would be difficult to solve. So here you see kind of another example. The robot is throwing the bottle into the waste basket. So it's again updating it. And in the belief state, it just loses the attachment of the milk box to the hand. But by that and the physics simulation of the virtual reality, it can infer where the milk box is after it dropped it, right? And so I think it's kind of very cool to combine the internal simulation with kind of updates of the belief state, and basically then get a belief state which is much more continuous. And we are pushing in that direction. So we also want to basically have the update of the belief state during manipulation actions, but we are not there yet. Okay, so the other thing is, so we basically have the belief state as a symbolic knowledge base, but we do not only want to have the symbolic knowledge base, the belief state, so the state of the environment as a knowledge base, but we also want to have the whole activity kind of the person. And we have seen that. Just show you the first part of the video where we see, so here what you see is we are taking the belief state of the robot, which in its symbolic form, and asserting it to the inner world model. So here you see that it's essentially a prolog query that we are executing, and we use it for populating the world environment. Then, based on the belief state of the robot, we can ask a person perform a particular task in the inner world model using a virtual reality setup. So here, Andre is basically asked to set the table, and we are interpreting in the physics simulation of the virtual reality demonstration in order to find the force dynamic events like the contact of the hand with the handle and the state of the and the object being picked up, and that allows us to pass the activity in the virtual reality using a CRAMA for fetch and place actions in a symbolic representation, right? And you see here always the symbolic representation that is questioned, and here the sub-symbolic representation of the answer to this query. And you can see when the human is executing this action that we get updates of that. And that was a part we have seen before, and that gives you kind of all the sub-symbolic information. Another component we can do if we have that inner world model is to do mental simulation and prediction. So what we have developed is a simulator, just as the robot simulator Gazebo, but with the difference that the scene that the robot is acting in is a rendering of a symbolic knowledge base, and that if we have executions of robot plans in the simulated environment, they are automatically passed, as we have seen just before, and put into symbolically annotated and structured episodic memories. So here you see the robot executing essentially the plans that we have seen for the table settings scenario, you see that the behavior of the robot is pretty much similar, and components of the system of the overall control system are run in the same way in the simulation here. But again, for me, the most exciting thing is that whenever we are visualizing something as a virtual reality scene, it's a symbolic knowledge base, and the robot has all the knowledge about the scene. So if the robot is able to compute with its perception system a scene that looks like the reality, it's such that the robot at that point pretty much understands what's in the real world and can plan its actions based on that. Okay. So one task is, of course, that, and that is a critical one, whether we can basically maintain the belief state while the robot is accomplishing a task like setting the table. And we are doing that by completely rewriting our perception system such that it's maintaining a belief state. And so we are realizing an expect, validate, correct cycle. So the idea is that the robot is a computing its expectations and compare them in order to validate